Chapter 14, Aqueous Equilibrium, Acids and Bases. In the previous chapter, we discussed the principles of chemical equilibrium. We'll now apply those principles to aqueous solution of acids and bases, perhaps most familiar of all chemical compounds: acetic acid in vinegar, citric acid in lemons and other citrus fruits, magnesium hydroxide in commercial antacids, and ammonia in household cleaning products are among the acids and bases that we encounter in everyday life. Hydrochloric acid is approximately 0.15 molar concentration in acid in gastric juice. It is essential to digestion and is secreted by the lining of our stomachs in quantities of 1.2 to 1.5 liters per day. The characteristic properties of acids and bases have been known for centuries. Acids react with metals such as iron and zinc to yield H2 gas, and they change the color of plant dye, litmus, from blue to red. By contrast, base feels slippery, and they change the color of litmus from red to blue. When acids and bases are mixed in the right proportion, the characteristic acidic and basic properties disappear, and new substances known as salts are obtained. Before examining the quantitative aspects of acid-base equilibria, that is, how to calculate equilibrium concentrations in solutions of acids and bases, we need to ask what it is that makes an acid and a base a base. We first raised those two questions in section 7.5, and we'll now take a closer look at some of the concepts that chemists developed to describe the chemical behavior of acids and bases. An enormous amount of chemistry can be understood in terms of acid-base reactions, perhaps the most important reaction type in all chemistry. Thus far, we've been using Arrhenius' theory of acids and bases. According to Arrhenius, acids are substances that dissociate in water to produce hydrogen ions, and bases are substances that dissociate in water to yield hydroxide ions. Thus, HCl and H2SO4 are acids, and NaOH and BaOH2 are bases. The Arrhenius theory accounts for properties of many common acids and bases, but it has important limitations. For one thing, the Arrhenius theory is restricted to aqueous solutions. For another, it doesn't account for the basicity of substances like ammonia that don't contain OH groups. In 1923, a more general theory of acids and bases was proposed independently by the Danish chemist Johann Bronsted and the English chemist Thomas Lowry. According to the Bronsted-Lowry theory, an acid is a substance, molecule or ion, that can transfer a proton, H plus ion, to another substance, and a base is a substance that can accept a proton. In short, acids are proton donors, bases are proton acceptors, and acid-base reactions are proton transfer reactions. To see what's going on in an acid-base reaction, keep your eye on the proton. For example, when Bronsted-Lowry acid HA dissolves in water, it reacts reversibly with water in an acid dissociation equilibrium. The acid transfers a proton to the solvent, which acts as a base, a proton acceptor. The products are the trigonal pyramidal hydrogen ion, H3+, the conjugate acid of H2O, and A-, the conjugate acid of HA. In the reverse reaction of H3O+, in the reverse reaction, H3O+ acts as the acid, take 3. In the reverse reaction, H3O+ acts as the proton donor, the acid, and A- acts as the proton acceptor, which is the base. Typical examples of Bronsted-Lowry acids include not only electrically neutral molecules such as HCl, HNO3, and HF, but also cations and anions of salts that contain transferable protons, such as NH4+, HSO4- and HCO3-. When a Bronsted-Lowry base such as NH3 dissolves in water, it accepts a proton from the solvent, which acts as the acid. The products of the hydroxide ion OH-, the conjugate base of water, and the ammonium ion NH4+. In the reverse reaction, NH4+ acts as the proton donor and OH- acts as the proton acceptor. For a molecule or ion to accept a proton, it must have at least one unshared pair of electrons that it can use for bonding with a proton. As shown below by the following electron dot structure, all Bronsted-Lowry bases have one or more lone pair of electrons. Note that hydrogen ion H3+ can be regarded as the simplest hydrate of the proton. It can associate through hydrogen bonding with additional water molecules to give higher hydrates with the general formula, see this, such as H5O2+, H7O3+, and H9O4+. It's likely that acidic aqueous solutions contain a distribution of these ions, having different values of N. In this book, we'll use the symbols H+ aqueous and H0 aqueous to mean the same thing, namely, a proton hydrated in an unspecified number of water molecules. Ordinarily, we'll use H3O+ in acid-base reactions to emphasize the proton transfer character of those reactions. Some example problems. See next video for 14.2.